This video is brought to you by ROHM Semiconductor. Hello, today I'll be experimenting with wireless power transfer using NFC. I think most of you have probably heard the term NFC before. It stands for Near Field Communication, a short-range wireless technology that operates at 13.56 MHz. In everyday life, NFC is used in things like transportation IC cards, such as Suica in Japan. Suica and similar contactless cards use Felica, a technology in the NFC family. At its core, NFC is a wireless communication technology designed for data exchange, but it also involves the transfer of small amounts of electrical power during operation. That's exactly why transportation IC cards can function properly without having a battery at all. Today, our goal is to push NFC beyond simple data communication and see if it can really serve as a practical power source in real-world applications. The key idea is that NFC can also transmit power. I'll test just how much power it can actually deliver. I've even built a demo device for the experiment. So let's dive in and see what happens. First, let's take a quick look at how wireless power transfer works. The basic principle is electromagnetic induction. Here, I have a coil and a magnet. When you move the magnet toward or away from the coil, the magnetic flux through the coil changes, which induces a voltage across its terminals. The voltage is generated by the change in magnetic flux, which is known as electromagnetic induction. This change in magnetic flux is key. If it's slow, almost no voltage is generated. But if it's rapid, a voltage is induced. That's the principle of electromagnetic induction. Now, let's replace the magnet with another coil. This is the coil. This larger coil will act as the transmitter, while the smaller coil we've been using will serve as the receiver in the system. Now, we'll run an alternating current through the transmitter coil. This creates a changing magnetic flux around the coil. As you bring this transmitter coil closer to the receiver coil, the receiver coil generates a voltage, just like it did when we moved the magnet earlier in the experiment. Depending on the orientations of the coils and how close they are to each other, the magnitude of the voltage that's generated changes. The same principle applies when charging your smartphone or using a Suica card. If the orientation is off or the distance is too great, it won't work. I attached LEDs to the receiver coil. As I bring the transmitter coil closer to the receiver coil, see that? As you can see, the LEDs light up when the coils get closer. Even without any wires connecting them, we can still transfer power. This is the basic principle behind wireless power transfer using electromagnetic induction. NFC power transfer works on the same principle. So far, we've looked at the principles of wireless power transfer, but there are actually several different methods. Here, we'll compare Qi charging with NFC charging. First, let's talk about Qi charging. Most of you are probably familiar with it, since it's commonly used for wireless smartphone charging. The main difference between Qi and NFC is the frequency they use. Qi operates between 110 and 205 kHz, while NFC operates at 13.56 MHz. There's also a big difference in how much power they can deliver. Qi can transmit a fairly large range, from 5 watts up to 25 watts, whereas NFC can only supply a few watts at most. The NFC module we're using today can supply 250 milliwatts. Compared to Qi, NFC can only deliver a small amount of power. When it comes to raw power, Qi clearly has the advantage, but NFC power delivery has its own benefits. One of these is that it allows for much smaller coils and more compact power delivery systems. As you can see, Qi transmitter and receiver coils are often around 50 millimeters in diameter. To further improve transmission efficiency, magnetic materials like ferrite are sometimes used as well. As a result, the overall system tends to be larger, which is an unavoidable drawback. On the other hand, NFC has benefited from higher frequencies, allowing both the power transmitter coil and the receiver coil to be smaller. There are also differences in data communication. Qi charging includes control communication to monitor the battery status and manage the charging process, but it doesn't allow users to exchange arbitrary data between devices. NFC charging, on the other hand, is built on NFC technology, so it can be used not only for power delivery but also for exchanging user data. I'll be demonstrating this later in the video. As we've seen so far, Qi charging and NFC charging have very different characteristics, which means their applications differ as well. Qi requires relatively large devices that can accommodate a coil and deliver high power, like smartphone wireless chargers. NFC charging, on the other hand, is better suited for small devices such as smart rings, fitness bands, wireless earphones, and hearing aids. Next, let's take a look at how much power we can actually deliver using this NFC module. The module you've been seeing since earlier is an evaluation board built around an NFC wireless charging IC released by ROHM. The larger board on the left is the power transmitter, and the smaller board on the right is the power receiver. As for the model numbers, the transmitter is the ML7671 and the receiver is the ML7670. Since these components are mainly intended for use in small devices, they come in compact IC packages. In particular, the receiver is designed for ultra-miniaturization and uses a wafer-level chip-scale package. Let's also take a look at the coils. Because the boards operate at a high frequency and require only a small amount of power, the coils can be quite compact. The coils aren't made from copper wire like in Qi. Instead, they're formed as pattern traces directly on the printed circuit board. By the way, the antenna design is a critical aspect of NFC power delivery. Since it operates at a high frequency of 13.56 MHz, precise antenna matching is essential. However, ROHM works closely with antenna manufacturers to offer validated antenna designs, matching tools, and even reference designs, which significantly lowers the barrier to antenna development. By the way, there are already products on the market that use ROHM's NFC wireless charging ICs. One example is this smart ring, the Soxai Ring 2. This ring contains a battery that is wirelessly charged. This is how it charges. This ring uses ROHM's NFC wireless charging IC for its power section, the same one we've been using throughout this video. The IC we're using in this video is intended for consumer applications and can deliver up to 250 milliwatts. However, there's also an industrial lineup available that supports power delivery of up to 1 watt. So from here, I'd like to actually try wireless power transfer using NFC. Now, let's turn on the power. Actually, I can't. Because of radio regulations, I'm not allowed to turn on this device to generate a 13.56 MHz high-frequency magnetic field from the coil in this office. However, we're determined to carry out the experiment, so we decided to borrow a radio anechoic chamber from ROHM and run the test there. Now, we're inside the radio anechoic chamber. This is part of the EMC measurement facility at ROHM's Yokohama Technology Center, and we've borrowed a section of it for our experiments. Now, let's actually power up the evaluation board. I've supplied 5 volts to the power transmitter, and the light just turned on. As we bring the receiver module closer, the system negotiates the power transfer, and wireless power delivery starts on the receiver. I connected an LED to the receiver, and as I brought the coils of the modules closer together, the LED lit up. It's working perfectly. Next, we'll check the high-frequency magnetic field generated from the power transmitter module's coil using the oscilloscope. When you bring the probe close to the module like this, you can clearly see the 13.56 MHz high-frequency magnetic field. It's surprisingly distinct. This magnetic field is picked up by the receiver module's coil, rectified and ultimately converted into usable power. In terms of specifications, this evaluation board can deliver a maximum of 250 milliwatts. So now I'd like to run an experiment to see how much power it can actually draw. We'll conduct the experiment with a 3mm spacer between the modules like this. A resistive load is connected and a current of 1 milliamp is flowing. Let's increase the load. I'm adjusting it now. It says it's 2 milliamps now. Let's continue to increase the current. Now it's 10 milliamps are flowing now. This means we're currently transmitting 50 milliwatts. Let's increase the load further. Now it looks like this. As we raise the load, you can see that the current occasionally drops. In other words, there are moments when the voltage falls to 0 volts. This happens because the IC is adjusting the transmitted power, increasing the load further. It's now at 20 milliamps. This means roughly 100 milliwatts are being transmitted. Now it's 150 milliwatts. Now 40 milliamps, which corresponds to 200 milliwatts. Let's increase the load further. I might have gone a bit too far. It jumped to 70. Now 50 milliamps are flowing, which is roughly around 250 milliwatts. However, to supply 250 milliwatts, the gap between the coils and the charging conditions have to be just right. If the load gets too heavy, the power delivery drops out. In this case, a load current of around 30 to 40 milliamps, corresponding to roughly 150 to 200 milliwatts of power, was the upper limit for stable power transmission. Next, I'm going to build something using this evaluation board. Right now, I'm putting together a circuit on a breadboard. So today, I made a smart band as an application example of the NFC power module. Here it is. First, let me explain the setup. The system is roughly divided into 2 parts. This is the power transmitter, and this is the smart band worn on the wrist, which acts as the power receiver. The power transmitter uses the ML7671 evaluation board that we were experimenting with earlier. The smart band on the receiver side also uses the ML7670. The received power is converted to 3.3 volts by the battery module, which then drives the microcontroller, accelerometer, and display. First, we'll check whether the smart band can operate using only the power from wireless charging, without the battery connected. The coil alignment was a bit sensitive, so I used a spacer to fine-tune the positioning. When I powered it on, something appeared on the display. It shows the acceleration data from the 3 axes measured by the accelerometer. When I tilt the accelerometer, the values on the display change as expected, so it's working properly. As you can see, the microcontroller, display, and accelerometer are all running solely on wireless power. I chose low power components for the microcontroller and other parts here, but compared to the components used in commercial products, they still consume more power. Even with such components, the NFC module can provide a stable power supply. However, because it operates solely on wireless power, if the receiver moves away from the transmitter's antenna, the power supply will be interrupted, causing the device to stop functioning. This is how it works. It stops when moved away and starts operating again when brought closer. Therefore, when using wireless power methods such as NFC wireless charging in an actual product, it's necessary to pair them with a battery. So I tried adding a battery to the smartband. The battery has started charging. With the battery added, the smartband can keep operating even when it's removed from the power transmitter coil. When it's placed on the transmitter coil, it charges wirelessly, and when taken off to carry, it runs on battery power. It's very similar to typical wearable devices. So far, we've mainly used the evaluation board for wireless power transfer, but originally NFC was designed primarily as a method for data communication. For example, transportation IC cards can receive a small amount of power during data communication, but this ROHM device increases that to several hundred milliwatts, enabling practical wireless power delivery. So next we'll try using this device for data transmission. I've set up this experimental setup. The device on top is the smartband, and the one below receives data from the smartband. What this device does is send the accelerometer data from the smartband to the transmitter IC via NFC using the onboard power IC. That data is then displayed on the transmitter's built-in screen. When you hold it up like this, NFC communication has started. Data is being displayed on the receiver like this. And when I move the accelerometer like this, see that? The same data you see on the smartband is mirrored on the charger display. And that's it in action. What happens if we turn off NFC here? This is what you get. The display below uses a ring buffer, so it keeps showing the last value. If you bring the charger back up again, there we go. Data communication via NFC is working just fine. One important thing to note here, the wireless power IC in this device can't handle data communication and power transfer simultaneously. So during data communication, power delivery is temporarily interrupted. That means the smartband needs its own battery for data communication using NFC. However, ROHM also offers models like the ML7661 and ML7660, which automatically switch between power transfer and data communication. With those, data exchange is possible even without a battery. If you want to avoid using a battery on the receiver, and you're okay with data only being available while it's in contact with the transmitter, those models are a better option. This is a bit of a side note, but if you bring your smartphone close to the receiver board like this, it acts as an NFC tag. The NFC tag data is stored in the memory inside the ROHM IC. In my case, I set it up to open my YouTube video page. Data communication uses the high-frequency magnetic field generated by the smartphone's NFC antenna. The board still works with this field, even though it's for data communication, not for power. So today, I explored ROHM's wireless charging IC that uses NFC. Compared to Qi, NFC cannot deliver as much power, but it allows the antenna and the overall system to be made dramatically smaller. So this technology could be really effective for small devices like smart rings or earphones that need non-contact power delivery. For this video, I actually tried making a smartband. Because the circuit is relatively small, it was able to run smoothly, even with only 250 milliwatts of power. The model we use today can't handle data communication and power transfer at the same time. But there are industrial models available that can do both, so you can choose the one that fits your needs. Thank you for watching. See you next time.